In this video, I will explain the concept of the locomotion angle, an important piece of the strafing locomotion system puzzle, and it's a concept that we'll be coming back to and using time and time again throughout this series. Additionally, in this video, I'll show you how we can apply the concept to warp an animation so that its movement aligns with the character's movement direction, regardless of the difference between the two. In a strafing movement system, the character always has a target direction that they're facing, and their movement is relative to that facing direction. And because of this, we need to have a system that can figure out which of these animations to play at which time. Direction is an intuitive concept for us. We can understand the difference between the type of movement we'd want to apply when wanting to move forward and the type of movement we'd want to apply when moving backwards. However, we can't just tell the computer to play the backwards animation when we're moving backwards without giving the computer a way to understand what backwards means. And this is where the concept of the locomotion angle comes into play. The character has a facing direction, and they have a movement direction that may not align with this facing direction. The character is always moving relative to their facing direction. If our camera is pointed one way and we hold down the W key, we walk in the same direction as the camera faces. However, if we hold the A key down, we walk left relative to the camera, but not relative to the entire game world. So the simplest way we could encapsulate this concept would be to determine the relative angle of our movement from the reference point of the facing direction of our camera. This relative angular offset is referred to as the locomotion angle. When our locomotion angle is the same as our camera facing, or when we're moving forward, it is 0 because there is no offset. As our movement direction and camera facing direction diverge, the angle of offset becomes greater. At its maximum value, this offset will not exceed 180 degrees of magnitude. If we're only considering this offset in terms of its magnitude, then we lose the ability to tell whether or not we're moving left relative to our facing or right relative to our facing. We can account for this issue with a fairly simple fix. We do this by dividing our 360-degree circle that is our locomotion angle in half and multiply the left side by -1 and leave the right side positive. Our locomotion angle now fully aligns with a scale of -180 to +180, where both negative and positive 180 align with the backwards direction. Now that we understand what the locomotion angle is, I'll show you how we can acquire it within our animation blueprint, and then I'll show you how we can use it in one of the many different practical applications it has. I'll create a new function named getVelocityData, and inside of it I will place a property access node. Inside of this node I will select the velocity variable from our character movement component, and I will use it to set a new variable inside of our animation blueprint named character velocity. I'll plug this in, get the character velocity variable, and multiply it by 1 on the x-axis, 1 on the y-axis, and 0 on the z-axis. I will set this value as a new variable named character velocity 2D. I'll plug it in, and inside of this function's details panel, I'm going to make sure that it is set to thread safe. I'll compile and place this function inside of Blueprint Thread Safe Update Animation. Now I'm going to reorder these, but this is just a matter of personal organizational preference. Now that we have our velocity variable inside of this animation blueprint, I'm going to go ahead and use it to calculate the locomotion angle value. Now, the anim instance class actually implements this already for us with a function called calculateDirection. However, if you are interested in what the actual code and math looks like to get the velocity vector and base rotation and turn them into a locomotion angle float. Here is the code for this function on the screen now. I'll plug in our new character velocity 2D vector, and I'll go ahead and grab the world rotation rotator that we created in a previous video. I will promote this output to a variable named locomotion angle. I'll go ahead and connect this up, and before I move on, I'm going to add these two new variables to a category named velocity data. I will do the same for the getVelocityData function that we just created. Now that we have attained our locomotion angle, we can use it in a variety of ways. One of the most useful things we can use it for is to warp an animation's movement direction to align with our character's movement direction, and I'll show you how to do that now. The technique that I'm going to show you is called orientation warping. To use it, we need to enable a plugin. So I'll go to this Edit tab and select Plugins, and I will search Animation Warping. And this Animation Warping plugin needs to be enabled. In this case, I've already enabled it, but you will need to tick this box and allow the engine to restart to enable the plugin. I will make my way into the cycle state inside of our locomotion state machine, and if I right-click into this graph, I can place an orientation warping node. Now, this orientation warping node has a blue pose pin, which is different than the white ones that we've worked with so far, and that is because this node works in component space, while these nodes work in local space. When an anim graph looks at or works with a bone in local space, that bone's transform, its X, Y, and Z axis values, as well as its roll, pitch, and yaw, are all considered relative to the previous bone in the chain. For example, the hand bone would not be considered to be, let's say, 70 units above the ground in local space. It would be considered to be 10 units below the lower arm bone. Now, those units aren't exact, but they should do well enough to demonstrate my point. On the other hand, when working in component space, the animation graph considers the transform of every bone relative to the skeletal mesh component and does not take any parent bones into account as it considers their transform. This means that the hand bone, when considered in component space, would be 70 units above the ground, and it being 10 units below the lower arm bone has nothing to do with the way that the graph considers its transform. Some operations are easier to perform in local space. For example, many operations that are just rotating bones, it's easier to add rotation to one bone and allow it to still carry over and maintain the rotation of the previous bones in the chain. However, other operations are easier to work with in component space, and that's really all that it comes down to. If we have this context-sensitive option enabled and we drag off from a local space node and search for a component space node, such as this orientation warping node, it does not appear because it cannot be directly connected to a local space node because a local to component node needs to be created, which the engine will do automatically when we drag between the two. I will connect this orientation warping node to the output animation pose, and it takes two float inputs, an alpha and an orientation angle. I'm going to leave these alone for the moment and bring your attention to the settings for this node. This node requires some information about our character's skeleton because it is intended to be a general use node for a variety of different relatively humanoid skeletons. And not every game is going to be using a skeleton that has the same hierarchy and bone names as the default Unreal Engine 5 skeleton. So I will give it the spine bones of this skeleton. So from spine 1 all the way to spine 5. And now it is asking for an IK foot root bone and IK foot bones. I will search IK and select the IK foot root. I'll create 2 array elements here. I'll search IK, I'll select IK foot L for one, and IK foot R for another. A skeleton asset is made up of a hierarchy of bones, usually weighted to a character mesh, meaning that when a bone moves, the section of the mesh weighted to it moves as well. This is how characters are generally animated in games. Now, an IK bone is just a bone that exists as part of a skeleton, but is not weighted to any part of the mesh. And that is really all it is on a technical level. It's that simple. Where it becomes more complex or nuanced is when we consider the purpose that these bones are used for and the techniques that they enable us to use within our animation graph. There are 2 main ways to move a bone in a chain of bones to a target point. The first is to rotate each bone in the chain in order until the end bone aligns with the target point. However, if you're trying to do this, you'll quickly find that it's quite finicky and easy to not quite get there all the way or overshoot your target. The other way to achieve the same effect would be to directly move the bone at the end of a chain to the target point that you desire, and then apply an algorithm to determine the rotations of the preceding bones in the chain so that the bone that you moved and the bone at the beginning of the chain are connected properly by the bones between. The first method is referred to as forward kinematics, or FK, and the second is referred to as inverse kinematics, or IK. And that is the function that the IK bones in a skeleton are meant for. They're meant to act as target transforms for the normal weighted bones in the skeleton. The UE5 mannequin skeleton has IK bones for the feet and hands, as they're the most common bones that inverse kinematics are used with and applied to. They are meant to be animated along with the standard bones in the skeleton so that in any given pose, the transform of an IK bone aligns with its target normal forward kinematic bone, which would allow us to alter the position of the IK bone at any point in our graph using any logic we wish, and then apply an inverse kinematic algorithm to that bone chain at the very end of our graph so that the actual weighted bone in our skeleton aligns with the inverse kinematic bone that we've been altering throughout the course of our system. And this is an extremely powerful tool. The orientation warping node that I've placed adjusts both IK foot bones in our skeleton to achieve its warping effect on the input pose. So to see the full effect of the orientation warping node, we need to align our forward kinematic feet bones that are connected to the rest of our skeleton with the IK bones that the orientation warping node has altered. So now that we're back and understand the IK bones usage and purpose, we need to tell the animation graph to actually use these IK bones and align the character's feet with them. I'll do so in the anim graph using a node called leg IK. This is another component space node, so it'll create these local to component conversion nodes when I plug it in between the locomotion state machine and the output pose node. This node requires leg definitions for the legs that our skeleton has. I will create 2, and inside of one, it requires an IK foot bone and an FK foot bone. For the IK foot bone, I'll select the left foot. The FK, or forward kinematic foot bone, is just the normal foot bone of our character, so I'll select the corresponding left foot bone. For the second one, I will do the same, but for the right foot. So IK foot R and foot R. Now, the rest of these settings are correct for this mannequin skeleton. However, eventually, if you are working with your own skeleton or different ones in the future, you may need to alter these settings when you use this node so that they line up with your own skeleton properly. I will go ahead and compile, and actually, I almost forgot, back in this cycle state, let's go ahead and hard code an angle in here. I'll put in 45 degrees. I'll compile again, go back into the third person map, and if I press play and walk forward, you can see that our character's legs rotate 45 degrees, and while it doesn't line up with our movement, but it is warping the angle of the animation by the amount that we specified. Now, this is important to understand. If I were to plug in the locomotion angle directly, it would work with this animation, but not an animation that moves in any other direction. If I open the asset browser and search jog loop and select this backwards jog loop animation and drag it in, I can create an animation sequence player with this animation selected. I need to make sure it's looping, and if I plug it in, you can see that the orientation is warped when I move, but it is not warped properly. That is because it is rotating by our locomotion angle from a starting point of 0 degrees, but the backwards animation isn't at 0 degrees by default like the forward is when we are considering it in terms of its locomotion angle. It is at 180 degrees. So to drive its orientation angle, we need to offset our locomotion angle by the locomotion angle of our animation. And that is how we provide the orientation warping node with the correct angle to use with an animation. We subtract its locomotion angle from our locomotion angle that is calculated from our velocity and rotation. Now, if I move backwards, the character's animation aligns properly. Now, the next step is to switch between these two animations based on our locomotion angle. I'll disconnect this backward loop from our local to component node, pull these back, and I'm going to search for a blend by bool node. And this node takes in a true pose, a false pose, and switches between them based on this active value input. In this case, I'll copy the locomotion angle variable, paste it, and I'm going to check to see if it is less than 90 degrees. And I made a mistake here. I actually need to get its absolute value. And this is effectively dividing this locomotion angle's circle from -180 to +180 in half along the horizontal line through the middle. So if I plug this in and then plug this into our output animation pose, compile and play, if I move backwards or within this lower hemisphere of the circle, the backwards animation plays, and we switch to the forward animation when I move in this forward or upper hemisphere from -90 to +90. Now we need to apply orientation warping to these animations, and I could take this orientation warping node group here, duplicate it, and run each of these animations through it, but there's actually a different mode that this orientation warping node can operate in. I can select it and change its mode from manual to graph, and you can see that this input changes and it reads locomotion angle. I can plug the locomotion angle in directly, and I'm going to place this orientation warping node between this blend poses by bool node and the output animation pose node for the state. If I compile and play, you can see that it automatically figures out the proper way to orient the character based on the animation data of the animation or the pose being output from this node. And it is doing so by observing the root motion of these animations. If I click into this backwards jog loop, to use it as an example, and I uncheck force root lock and uncheck enable root motion, we can see the fully animated character. This root bone here is moving with the character. The orientation warping node can observe its movement and infer a locomotion angle for the animation from it. However, not every animation has an animated root bone, so you may need to use the manual mode on the orientation warping node when using it with animations that do not have animated root motion. I'm going to go ahead and enable root motion so that the animation graph can process the root motion and use it to inform the orientation warping node. And I'm going to recheck this force root lock as well. I can save this and close out of it. And now, finally, I'm going to change the blend time for this node to, I think, 0.2 or 0.3 actually, I believe are good values for these two animations. And there are some settings here that you can alter further, and I encourage you to explore. Specifically this blend mode here, because there are varieties of different curves that can be followed for the interpolation between these two animations. Personally, I like Hermite cubic in-out for these two animations, but definitely play around and explore these blend modes here. Actually, if I go back to this Locomotion state machine and select these transitions, the exact same blend settings appear, and these are universal settings that nodes that blend between animations use, and I will be covering these settings in much more detail in the future as we have more nodes to blend between and they become more important in our system to achieve the look and feel that we desire. Now, if I play and move around, the blending between states is a bit less fast and seems a little bit more natural. Now, I want you to observe what happens if I move at 90 degrees and rotate my camera slightly. The character continues to cross that hemispheric threshold that we defined, and so it switches constantly between these animations, and that isn't very natural movement. To fix this, we can add a dead zone. However, that is going to be part of what I cover in the next video. In the next video, I'll expand this fairly rudimentary system for switching between animations into something that's much closer to being complete, as well as include more animations within it so that we can achieve a higher fidelity in the look of our character as it is moving around. If you have any questions, be sure to leave them in the comments or in the Discord server that is linked in the description below. I'll answer them as soon as I'm able to, or directly in the next video. I'll see you there.